Okay, so this is project number 3 spec, and the outline is exactly the same as all the previous two previous projects, and the link will be the link to the Google that will be shared in class and after this class. So as I said, the third project will be, the objective of the third project will be image classification. So the objective is, given a chest X-ray image, you need to predict all positive diagnosis labels, because a single image, a single chest X-ray image, might be associated with multiple diseases. You know, someone might have pneumonia and tuberculosis at the same time, or something, you know, basically. So it's, again, it's a multi-label prediction task. And so you need to construct the multi-label image classifier for prediction, and you could consider any kind of image encoder. It could be ResNet or WideNet or whatever you want. It's so the spec. Yeah, there is not a specific spec for the model architecture or the pre-processing of the image. You can do whatever you want. The data set is called Mimic CXR JPEG. So let me click this actually. So you can download the data from here. Here there are files and there are metadata. There are some labels called neg biochecks. We'll talk about this. So you can read the details about the data set here. There's abstract background, methods, label, and all that. And yeah, please use this link. And so in order to do image classification, you need the images and the ground truth label. So, and the images are each. So this is the structure of the Mimic CXR JPEG data set. So there are files. Like just like here, there are files here. So each patient has potentially a multiple. So the whole thing consists of multiple patients. So this Mimic CXR data, Mimic CXR images are collected from multiple patients. I forgot how many patients, but I don't know, maybe tens of thousands of patients. So multiple patients, and each patient has multiple studies. So each patient can potentially have more than one study. So each study is a single trip to the radiology department. So each study, so again, so the top layer is patient, the second layer is study, right? So for each subject, so each subject ID, this means patient. For each subject ID, there can be multiple study IDs. So for example, here, if you look at here, so this is the files, and this is there are 10 subsets, 10 files or 10 folders that cover all the data sets. So in the P10 folder, there is patient number P100000032. So this is the subject ID. And this subject ID consists of 4 study IDs, 4 studies. So this is study number 1, S50414-67. This is the second study, third study, and the fourth study, right? And each study, exactly. So what we're, in this study, we're only using one, in this project, we're using only one study per each patient. So here, even though there are 4 studies for this patient, we're only gonna use one study, which is that comes alphanumerically the first, this one. So extract only one study ID per subject ID. This is what it says here. If there are multiple studies for a single subject ID, select the one with the lowest alphanumeric study ID. So the one that comes first, which is here, because S5050 precedes all other study IDs, which is S53, S53, S56. And each study ID contains one or more CXR images, one or more. So here, as you can see here, this study ID contains 2 images. This study ID contains 2 images, but this study ID contains 1 image. So in this case, when a single study ID contains more than 1 CXR image, you will use only 1 CXR image again. So the reason that each study ID might contain more than 1 CXR images is because each image might have different view positions, such as like the frontal view or back view or side view. When you go to the radiology department, when you take an X-ray, sometimes the doctor or the engineer in that room might ask you to like stand up, lie down, turn your back, or something like that. So to take multiple positions, to take X-ray images of multiple positions. So that is why a single study might have more than one image. So that is called APPA lateral. And in this project, we only use AP view images. So if there are multiple images in each study, you only select one AP view and that's it. So extract a single AP view image from each study. So if there are multiple AP view images, select the one with the lowest alphanumeric file name. So for example, in here, if these two were both AP view, which is the frontal view, if these two images are both AP view images, then you are going to use this one, because this ID, this file name comes before this file name, alphanumerically. This started with 02, this starts with 17. So you select only this one. I mean, when these two are both AP views. But in other scenario, if this is lateral view and this is AP view, then you select this one. You select this one, right? Right. So how do you decide which? So this is just JPEG image. So how do you know that this JPEG image is AP view and this is not? So that depends on the metadata here. So this metadata. So if you download metadata and unzip it, and if you open metadata, actually let me open it for you. Let me share. So when you open the metadata, it looks like this. Looks like this. So there's in the top row, there's a column. So there's DICOM ID, subject ID, study ID. What you need to care about is study ID, obviously. So in study ID, which is here, this is the study ID. There is something called view position. So that is 1, 2, 3, 4, fifth column. There's fifth column view position, which is 1, 2, 3, 4, 5. Fifth position here. So this says PA. So this is not what we want. We want AP. So when you go through the study IDs, you look up the study ID in this metadata and see if its view position is AP. Oh, I'm sorry. You also need the DICOM ID, which is the file name. So here, actually, yeah, it's really hard to share it. So let me stop sharing. All right, when you go to, when you see the actual file name, the file name is called DICOM ID. So this is the file name. So go, remember how it looks like, and then I'm going to share the metadata again. So this is the corresponding file names. So when you go through the study IDs and there are multiple files or multiple DICOM IDs for each study ID, you come here to the metadata to look up what the view position of each file is or each image is. So if your image ID is this, then you go to the fifth column and look at the fifth column value, which is AP. So that is okay. But if it's lateral or PA or something else, that we exclude, we just throw them out. Okay, cool. Hopefully this is clear. Well, going back to the Google Chrome. So as I said, if there are multiple AP view images, select the one with the lowest alphanumeric file name, or file name meaning DICOM ID. Right, so this is how you select for each patient only one study ID, and for each study ID only one image, one AP image. And as for the labels, you look at this file name, which is right here. This one. This is your file name, and this is the label file. So this file contains multi-label information for each study ID. So each study ID, so not patient ID, each study ID. So each study ID comes with a unique set of multi-label, and I'm going to show you the value actually. So when you open the file negbio, it looks like this. So there's subject ID, there's study ID, then there's a whole different number of columns, which corresponds to each disease name. So atelectasis, cardiomegaly, consolidation, edema, enlarged cardio, whatever, fracture, lung lesion, lung opacity, what, yada, yada, yada. So I think there were like 13 or 14 columns. So what you need to do to get the label for each study ID is come here to the second column, which corresponds to the study ID. And then all the following values are labels. So if there is nothing, for example, here for atelectasis, there is nothing here. So that means that it is neither, oh, actually, yeah, there could be 3 different values. So there could be 1 or -1 or 0. So what does that mean? So if a specific column is 1, it means that that disease is positive. So it means that this person, this study ID has a positive diagnosis for that column. But if it's 0, it means it's negative. It means that the patient, if the physician said this study ID does not have that diagnosis. If it's -1, then it means that the physician decided for this study that diagnosis is uncertain. So we're going to go back to the Chrome. So for each column or each diagnosis, it could be either 1 or 0 or -1, which respectively represents positive, negative, and uncertain labels. And if it's blank, like I've shown you just now, if it's blank, it's neither of these 3. So it means it's just nothing. But so in this project number 3, we're only going to use positive labels. So we're only going to consider the columns with value 1, and the columns with value 0 or -1, we're just going to throw them out. So we're only going to use column with value number 1, and that's it. So if a specific study ID does not have any positive value, then it's just simply all negative. It's all just, it's just, the prediction model should just output 0 for all the columns. And actually, let me just count how many columns there are. So there's 1, 2, 3, 4, 5, 6. 13, 14. Yeah, I think there are 14. Oh, I'm sorry. I think there are, let me see. No. Why can't I count it? Give me just a second, please. Yeah, there are 14 labels. So your multi-label dimension would be 14-dimensional. All right, so yeah, only use positive labels. And feel free to pre-process the image as you see fit. So, but the minimum resolution is 256 by 256. So this is, we're setting the minimum resolution for image to guarantee a certain level of performance. If you use image resolution of 32 by 32, then you will get a really low performance. I'm not sure if it'll actually be able to predict anything. So please, besides the image resolution, you can do whatever you want with the image. You can either normalize them or do like augmentation and whatever. But the minimum requirement is the resolution should be at least 256 by 256. And note that each image is they have all different proportions. So it could be like either 1024 by 512, or it could be 800 by 600, or it could be 256 by 1000, something like this. So each image has a different ratio or resolution ratio. So you need to consider how you're going to deal with that. So things to consider is first of all, as I said, image resolution. So we recommend using the image resolution between 256 and 256 or 512. But this is just a recommendation. As long as it is at least 256 and 256 by 256, it's okay. And Another thing to consider is pixel value normalization. So usually what people do is they normalize images by the ImageNet mean and standard deviation, but you can do that as well. But since this is black and white image, you can come up with your own mean and standard deviation, or you can simply not normalize at all if you want to. That's all up to you. And another things to consider that you might want to consider is class imbalance. So because among 14 labels, the 14 labels are not, not uniformly distributed, obviously. It's like some labels occur way more often and some labels occur really rarely. So you might want to consider the ratio between the different classes. So if you think that is a problem, you can reweight the loss functions or something like that. Or maybe you can undersample or oversample some labels specifically. So yeah, the labels. So in this assignment, you don't need to care about subject ID at all. As I said, the only thing that matters is study ID. For each study ID, it comes with a unique set of multi-labels. So each study will be treated independently. And therefore, you only need to care about study ID and extract, as I said, extract only the positive labels for each study ID from this file. And data split is as usual. Studies with whose study ID ends with digit 8 and 9 should be left out as test set and use the rest of the samples as our training set. So study ID is, as you see here, study ID ends with a number. So if it's 7, this is training sets. This is training set. But here, actually, we're only using one study ID from each patient ID. So we're only using this study ID. And this study ID ends with digit 7. So this becomes the training sample. And the data format. So this time we don't require you to upload the training feature and the training label. We only require you to upload test features and test labels because we're not going to evaluate the training performance at all. So you can pre-process this data set so that your pre-processing code produces X test pickle, or it could be NumPy, it could be anything actually. The format of this file doesn't really matter as long as you just have features encoded that can be used by the evaluation script. That's okay. So this could be anything. Your input features must contain the actual input of your test model.py as usual. And you can use any type form. It could be pickle, it could be NumPy, it could be text, whatever. And the label file actually needs to be specifically the text file. So it has to be txt. Each row, as project number 2, each row contains study ID followed by multi-labels, all comma separated. So study ID, this, and then labels for your 14-dimensional multi-label. Must be a text format. In order to confirm that you have pre-processed data correctly, we'll check the number of positive labels in this file. So that will be the way to check your pre-processing step. And modeling evaluation, you can use whatever model you prefer. We recommend using Resident 50, but you can use whatever you want. And we're going to use both AURC and AUPRC as before, as project number 2. Use both AURC and AUPRC and both macro and micro to report your performance. And what to submit is, first of all, you should, if you're using your own unique set of packages, you should submit your requirements.txt. So submit this. Do not make any subdirectories. It all is the same for all submitted, all the deliverables. Do not make any subdirectories as usual. So requirements and feature and label files. So feature file like this, but you can use any type format. Label file as described, and do not make it again. It should be in the same directory. Model parameters as usual, and test model.py as usual. And this model.py, this script should be using these two files, xtest and ytest, to evaluate to report the test performance of your model. As usual, command must be this, and this should internally load the data set, both the test and the xtest and ytest, and the model parameters internally using relative path. And your code, as usual, should generate this file, which contains these 5 lines. So the first line should be your student ID, and then the following are test macro AURC, test micro AURC, test macro AUPRC, test micro AUPRC, and that's it. and you should zip all your deliverables, this, and these. So all the deliverables into a single zip file that has your student ID as the name. So student ID, tarball, gunzip. Right, and then please, instead of uploading it on KLMS because of the potential size issue, you should upload your student ID. You should upload your submitted file, your zip file, onto your Google Drive, and then submit the Google Drive link, shared link, specifically shared link via KLMS. So upload this to the KLMS, and that's it. And the assignment evaluation is exactly the same as before. So if you just simply submit something, like even if it's empty file, you get 5 points. And then if you correctly pre-process the data set, you get 10 points. And if your model shows reasonable performance, 15. If you outperform TA, it'll be 20 points, and no late submission. And the TAs for this project number 3, it would be Taeyong Lee and Won Shin, and their respective email addresses are here. So among all 3 projects, this one should require minimum amount of pre-processing actually. So hopefully no one will be confused about how to set the labels and all such and such, because the label file is already provided in this file. You simply need to extract them. So hopefully this is the easiest project out among the 3. All right, so any question? All right, question from 안성용님. 인풋 필요한 입력으로 들어가는 엑셀 사진. 네, 그거는 네, 뭐 원하는 대로 하시면 됩니다. 그러니까 어쨌든 간에 JPEG을 뭐 따로 뭐 텐서화 시켜가지고 저장을 하시든 아니면 JPEG 자체를 저장하시든 그거는 뭐 근데 당연히 이제 X테스트 파일에는 모든 테스트 파일이 다 들어가 있어야겠죠, 당연히. 그러니까 이제 뭐 로우 바이 로우로 아마도 로우 바이 로우로 들어가 있어야 되는데 그 각 로우가 뭐 JPEG의 픽셀 이미지, 픽셀 밸류가 될지 아니면 뭐 이미 어떻게 뭐 프리프로세스해서 뭐 어떤 다른 방식으로 돼 있을지 그거는 알아서 하시면 됩니다. 혹시 이해가 되셨나요, 성경님? 그러니까 이미지를 저장을 하시더라도 그걸 X테스트로 다 넣어서 저장을 하셔야 된다는 거죠. 그러니까 그거 하나만 불러올 수 있도록 테스트 스크립트가 테스트 모델 그 파이썬 파일이 X테스트를 이제 불러올 때 거기 안에 이미 테스트 샘플들이 다 있어야 되는 거예요. 네, 좋습니다. And Soros, when is the deadline? So deadline would be 2 weeks, about 2 weeks from now, which is, I would say, yeah, that will be 17th of June, June 17th, which is the finals week. So we'll 17th of June. I'm not sure. I think it needs to be a little bit earlier than that, depending on when is the deadline for submitting the final grades, and we should consider the claims period as well. So if we'll announce the official deadline on Classroom after this class. No, I'm not. Let me see. No, I suggest you use PyTorch because the TAs will have PyTorch machines ready. I mean, yeah. If people start to use different like frameworks like MXNet, PyTorch, TensorFlow, you know, all these, then it will be really hard for the TAs to evaluate the submitted deliverables. So please use the PyTorch. But you can use whatever package you want as long as it's like common package. You can write them in the requirements.txt. All right, any other question? Nope. Yeah, I think this is a pretty straightforward task compared to the mortality prediction in project number 1 and the automatic coding in project number 2. Like those, like typically text and structured codes are harder to pre-process. Images are relatively easy actually. So hopefully this will be you guys will have like easier time for this project number 3. All right, so if there are no more questions, I'll see you guys next Tuesday, which will be the Q&A session. And I'll upload the details of the project number 3 on Classroom after this class. All right, thank you guys, bye-bye.